Hi all, the purpose of this video is to start with the Lorentz force to explain why Lenz's law is as such. So our learning goals are to know that the Lorentz force, to know that Lenz's law can be explained by the Lorentz force, and to know that Lenz's law is a phenomenological description that helps one determine induced currents. Okay, so let's say that we start with a bar magnet. There's a north pole, south pole, and because of that we're going to have B field lines coming in, looping around, so they never stop, they just always kind of make loops. This is something you should be reasonably familiar with. So now what we're going to say is that we also have a loop, a wire loop, right here, that's going to be moving down with a velocity v. So we have a loop of wire that if we dropped it all the way, it would ring right around the bar magnet, but it's falling at a constant velocity v, and because of that, we can now figure out the Lorentz force on different parts of the wire. So we just need to remember what the Lorentz force is. So the Lorentz force for a charged particle in a magnetic field is QV crossed into B. So what we can do is we can redraw this loop of wire, but from a very edge-on view, so it's just going to look like a flat piece. So this is just the loop of wire, but we're looking at it so that we only see the edges. So both of these are coming down velocity v. So both those have velocity v. And then what we need to do is we need to figure out the magnetic field at these points. So this point over here is going to correspond to a point over here. So let's call this 2. So that's 2. And the B field over here roughly points to the left. So for simplicity, we're just going to say it's to the left. Now, if we look at point 1, which we'll say is here, and will be over here, point 1, the B field there is mostly towards the right. So we have a B field here, it's towards the right. So now what we need to do is figure out the direction of the Lorentz force. So if we take our fingers and we point them in the direction of the velocity v, and we turn our hands such that we can close it in the direction of B, what we see is that the Lorentz force at point 1 will be coming at us, so that's F. And then if we do the exact same thing here, so that's F1, and then if we see F2, it'll be going into the page. Now, if we redraw this loop, that was a very horrible circle. So if we redraw this loop and we say that this is point 2 and this is point 1, the force here, the Lorentz force here, will just be in this direction, and the Lorentz force here will just be in this direction. So what ends up happening is that we get a net flow of current that's going to go around the loop like this. So that's going to be I induced. And now what's going to end up happening is if we have an induced current this way, then the induced magnetic field, due to this induced current, if we wrap our fingers in the direction of this current, our thumb will point in that direction, and then that will be this way. So this is B induced. So now we can ask ourselves, what would happen if instead of coming towards this, we were going away from it? So what would happen if the loop was going upwards instead of downwards? Then what would happen is the velocities would flip directions, the forces would flip directions, and we would be going the other way, and the B induced would be coming out at you instead of going into. And this is more or less a description of Lenz's law. So if we write down the magnetic flux, E dot A, then what we can say is, from Lenz's law, what we see is that nature wants the magnetic flux to be constant. So this loop has some area A and it has some B field B going through it. So if we move it down towards the magnet, then we're increasing the flux, and the current is in our direction such that it will oppose that increase in flux. And if we do the opposite and we pull it away, then we'll see that the current is in our direction so that it'll try and increase the flux, always trying to keep the flux the same. And this is Lenz's law, and now we see that we can just explain it in terms of the Lorentz force. But that's a little bit more time consuming if you just use Lenz's law. Thank you.